Hello everyone, we will introduce our project assessing CNN models for detecting potentially unauthorized architecture via oblique UAV images. We have 5 parts. Okay, the first part is introduction and problem description. The rapid urban expansion presents challenge such as the increasing of unauthorized structure currently, the effectiveness of various CNN models in detecting buildings is under researched and the use of UAV oblique images for computer vision analysis remains unexplored. Our project seeks to develop and assess 5 CNN models that use oblique images from UAVs to identify high-risk unauthorized buildings. The strategy will help governments focus their inspection more efficiently and enhance urban development and safety.
As for the algorithm we used, we have two-stage detector like faster RCN, also mask RCN, a single-stage detector like YOLO VA. Faster RCN first use anchor works to predict where objects are located in an image. It then classifies these objects using a feature extraction method based on the VGG16 architecture. This process includes a region proposal network and ROI pooling to fine-tune the object detections. Mask RCN builds on faster RCN by adding a feature that generates masks, using a ResNet backbone for even more robust feature extraction. It replaces RO pooling with RO align, enhancing the precision of object segmentation. UNet processes images through a sequence of convolutional layers and max pooling. It then employs unsampling to help segment image accurately, identify unauthorized construction with high precision. YOLO VA is a single-stage detector known for its speed, while traditionally less accurate than two-stage model. The YOLO VA has significantly closed the accuracy gap. Next, YOLO employs neural architecture search to fine-tune its performance, making it ideal for environments that demand quick analysis. This model dynamically adapts its architecture to optimize both speed and accuracy, enhancing its effectiveness in various scenarios. As for our simulation plan, first step is data collection. We gathered around 20 gigabytes of images from heights of 75 to 100 meters, capturing various angles between 30 and 75 degrees. We annotate this comprehensive dataset for later training purposes. The second step is annotation and pre-processing. Our team standardized the annotation process with a detailed guidelines, resulting in 656 oblique images. We allocated 79 of these images for training, 10% for validation, and 11% for testing. Last but not least, training and evaluation. We trained each algorithm on this dataset independently. Following the training phase, we assess the performance using metrics such as precision, recall, and F1 scores.
Next part, the results. As urban landscape continue to evolve at a rapid pace, the task of identifying unauthorized building has become important. This project has evaluated the effectiveness of 5 CNN models in detecting potential unauthorized structures. The dataset consists of oblique images captured by UAVs in Surrey. The models were benchmarked in precision, F1 score, and recall metrics with a confidence threshold of 0.5. Next, we check out the table. This table shows the overall results. YOLO VA model outperforms other in precision, means its higher reliability in minimizing the false positives. It achieves a precision of 0.72 and F1 score of 0.64 and the recall of 0.58. And meanwhile, the YOLO-NAS model, which incorporates a neural architecture search approach, demonstrated best balance between precision and recall, leading to the highest F1 score of 0.74 and the most considerable recall of 0.79. This indicates its superior ability to identify a broader range of high-risk architecture without significant sacrifice in precision. Conversely, the fast RCN model shows the limited precision at 0.22. Though its recall of 0.39 suggests some capability in identifying relevant targets, the mask RCN, an extension of faster RCN, improve upon this result substantially, yielding a precision of 0.48 and a recall of 0.56, alongside an F1 score of 0.52, making it as a reliable method for such applications. The UNet model, typically known for its performance in semantic segmentation, achieved moderate results across all metrics with a precision of 0.41 and a F1 score of 0.47 and a recall of 0.53.
So the prediction results from left to right are YOLO, Mask RCNN, Faster RCNN, UNet, and YOLO-NES. So from the table, we can see the YOLO VX ability to process images in real time makes it highly reliable for applications where quick and accurate detection is pretty crucial. In the comparison images, we'll notice that YOLO V8 tends to focus accurately on the most likely objects without over-predicting, which minimizes clutter and false alarms. So mask RCN adds a segmentation mask that helps in precisely define the object boundaries. This is reflected in its moderately improved scores across all metrics. In the visual comparison, we can see how mask RCN provides more accurate shapes and cultures of detect objects, enhancing the clarify of what it is identified. So faster RCN, known for its detailed two-stage process, first proposing regions and then classifying them, shows lower performance in its settings. That is possibly due to its complex setup and slower processing time. In images, observe that where it can identify relevant areas, it struggles with precision, often marking areas that don't contain the target objects, and primarily focused for the semantic segmentation. The UNet is effective in detailed object outline. In the images, note how the UNet met delicate object boundaries more clearly, which is useful in scenarios where understanding the exact layout of space is essential. YOLO-NES module's high F1 score and recall indicates its efficiency in identifying a broader range of objects will maintain a decent precision. In the images, look for how YOLO-NES map includes more potential targets, demonstrating a wider detection scope compared to the other modules.
Conclusion. In conclusion, this paper presents 5 CNN to detect potentially unauthorized construction. The YOLO models provide rapid real-time detection capabilities, whereas UNet excels in segmenting and detailing urban structures. Fast RCNN and Mask RCNN offer precise object localizations, complement YOLO's speed with their accuracy. Integrating these models allowed us to efficiently monitor and manage urban environments by enhancing the detection and classification of unauthorized construction. However, the limitation of our analysis is our current use of a static threshold limits adaptability. Future work will focus on developing an adaptive threshold system to improve the model's responsiveness to diverse. Thank you.